Aloha! I know you're probably terribly confused at this point. I'm not Ethan Allen. Although I do make furniture, and the real Ethan Allen in Likeable Science, he doesn't make furniture. Some other guy named Ethan Allen makes furniture. So if you're not confused yet, we'll try and confuse you by the end of the day. But I'm Stan the Energy Man here for Ethan Allen on Likeable Science, which today we're calling Weird Science. And what I'd like to do today is talk to you a little bit about science that I've experienced in my career, flying airplanes and doing weird things like that, that maybe some of the things that Ethan Allen's not experienced with or doesn't normally have on his show that maybe I can share with you and talk a little bit and help you understand about science. So one of the things that I first did when I got in the military, I was flying airplanes, and I was flying fighters and high-speed airplanes that did a lot of maneuvering. And what happens when you're in a fighter airplane and you're doing a lot of maneuvering is you turn corners really sharp, and you do what we pull G's, which are G forces, gravity forces. So if you think about it, if you have a rock on the end of a string and you're spinning it around, the rock wants to fly off into space, and it wants to do that because of centrifugal force, or actually gravity, artificial gravity. That's the string is holding the rock in, but it really wants to fly away. Well, the same thing happens to you when you're in an airplane and you're turning a really sharp corner, and you're really what we call pulling on the pole. You're really pulling hard, and you're making your plane accelerate around a curve that makes it want to squish you down into your seat. So what actually happens to you physiologically in your body is all the blood wants to go from inside your brain down into your feet. And that's a really uncomfortable feeling. So what happens initially is if you don't have something and you're not trained to fight these G-forces, you'll actually black out and go to sleep. We call it doing the funky chicken, technically. That's the technical term for it, funky chicken in the airplane, because you'll go unconscious. So what'll happen, physically what happens to you is your eyes are very sensitive to changes in blood pressure. So what'll happen is as you start turning the corner really hard, if you're not ready for the G-forces and you're not fighting it, your eyes will start to kind of gray. You'll see kind of it just gets tunnel vision and the colors go away. And next thing you know, you don't see anything, but you can hear everything. You're still conscious, everything's going on. But right after that, there's not enough blood pressure in your head and you pass out. And like I say, you do the funky chicken, you're just sitting there going like this. So what we do in the airplanes and the fighters to make sure that you don't pass out is you put on this thing called an anti-G suit or a G suit. And the new fighters that pull even more Gs, those folks have even full body suits that help them keep their blood pressure up. So we used to joke that the best fighter pilot was about 4 feet tall, had high blood pressure, and a low heart-to-head distance, because that's what keeps your blood back in your brain, so when your heart doesn't have to pump too hard to keep the blood there. But what the G-suit does is it wraps around your body, mostly around your legs and your abdomen area, and you're connected to the airplane. There's a sensor in there that feels this acceleration as you're going around the corner, and it pumps a bunch of air into this G-suit, and the G-suit literally squeezes you. It's like having somebody hug you really hard around your stomach and around your legs, and it squeezes all your extremities, on your lower extremities, so that the blood pressure in your upper body stays high enough to keep the blood in your brain. At the same time, they train us so that we literally squish and go like that. If you ever watch somebody in a centrifuge that's going through the training, you squish down on your arms, you hold tight, and you try and keep all the blood pressure in your head as long as you can, and you get your turn out of the way, and as soon as you can let off on the G's, you let off and catch up with your breath and get caught up. But that's how you fight off the G's, the artificial gravity that gets built up when you're flying in a fighter. It's really an interesting experience, and if you ever get to go on a high speed thing at the fair that's really spinning fast, you kind of get a sensation of G forces, but those are about maybe 1.5 to 2 G forces on your body. The average fighter pilot can sustain 6 or 7 Gs pretty much for quite a while, for 30 seconds maybe. But airplanes can generate up to 9 or 10 Gs, and some of the pilots have to sustain 9 or 10 Gs for maybe a couple seconds and then back off to 6 or 7 Gs and back into 9 or 10 Gs. It's actually quite a bit of work, and you can really pass out quickly if you're not right there with it. So the G-suit's really important and an amazing piece of technology, but it all starts with G-forces, anti-gravity forces. Another piece of science that I got to use in the military a lot was radar. And it's really cool stuff. It was invented probably just before World War II, around World War II. And for the first time, when you're out looking for another airplane or something, you can use your radar. But how does it work? It's like, okay, you have a radar dish that's that looks kind of like a parabolic dish, and it has a little thing in the end. It sends a signal out, and the signal is timed, and it hits another airplane, and then the signal comes back to the radar dish and gets bounced back to where it started. And there's a clock in here that measures the time it took for the radar signal to go out and the radar signal to come back. It does a whole bunch of mathematical calculations very quickly and tells you that this airplane is 30 miles away or 40 miles away or 10 miles away. And it helps the pilot situational awareness, so he knows where his enemy is, and he can do his maneuvers and adjust his position the way he wants it using the radar. Other neat thing about radar is it's great for navigation. You can use radar for navigation the same way you use it for the airplane, except that you can use it to look for a piece of land. Maybe you have a mountain in front of you and you don't want to run into it. So you just make sure that as you're looking out with your radar, you'll be able to tip the radar antenna up and down, and you can run it down. And as long as your antenna is looking level and you don't see anything in front of you, you know you'll get over the mountain. But if you're looking a little bit down and you see it just below you, it's like, oh, well, how far below you is that mountain? Well, we use a neat rule called the 60-to-1 rule. And what that means is for every 1 degree that you have at 60 miles, the object out there is 1 mile. So if this was 60 miles away, if this mountain was 60 miles away, and this was 1 degree on my radar scope right here, I know I'm a mile above the top of that mountain. And then if you were at 30 miles, you know you're at half a mile above the mountain. And if you're at 25 miles, or excuse me, 15 miles, you'd know that you're a quarter of a mile above the top of that mountain. So you basically use the 60-to-1 rule to help you calculate how much clearance you actually have. And when you're using round numbers like 60 or 6, it's real easy, because whatever the degrees are, that's how many increments of units of measure you are above or near that particular object. So that was a cool piece of science that really helped out a lot of folks, especially when it comes to weather. I talked to Ethan today about thunderstorms and how powerful they are. And airplanes don't like thunderstorms a whole lot, so we try and stay away from thunderstorms. And one of the ways we have to, just like looking at the ground, when you're looking at a thunderstorm, it usually starts at maybe 15 or 20,000 feet and may go up to 50,000 feet. So if you're in an airplane and you have that radar working and you go, okay, let me see, how high is that thunderstorm? How wide's that thunderstorm? How low? You can decide whether you're going to try and go off to one side and lower, or stay the same elevation and go around it. Or, hey, I can't get over the top of that. The top of that thunderstorm is so high, I can't get over the top of it. So they use a lot of the radar for weather avoidance, for looking for other aircraft and trying to figure out how far they are away from you and keeping a safe distance from them, and also navigation. And boats use the radar for the same thing on navigation. They can tell exactly how far they are away from a landmass, and even help identify where they are if they can identify certain specific mountains or land masses that they can match up on their chart. They can even help keep themselves oriented and keep themselves from being lost by looking at the radar picture compared to what they have on their charts. So that's another great piece of likable science and weird science that we got to use in the aircraft. I talked to Ethan earlier today about survival. That's a big thing in combat, or if you're in the military. You have to be able to survive, especially if your airplane decided to quit flying on you and you're stuck someplace. So some of the things that they teach us are how to tie good knots, how to put up a shelter, how to hunt for your own food or set up snares and make snares, how to make a fire, and how to do all kinds of things. But one thing that's really critical in any survival situation is finding water and being able to hydrate yourself, because you can go several weeks without food, but you can only go several days without water. And particularly if you're injured or you're doing a lot of exercise, like trying to get to a safe spot, and you're moving a lot, you're burning a lot of calories, you're also dehydrating yourself, you got to have a source of water. One of the ways that we would get water, especially if we didn't have a free-flowing stream or something, is we would take the water, take a piece of plastic, like a Ziploc bag or anything that we happen to have, like I just happen to have a Ziploc bag in my pocket, and you would take this, dig a hole in the ground, take the Ziploc bag or the plastic that you have and put it over the hole, put a small cup in the middle, put some weights around the end of the Ziploc bag to seal it around the hole, and then put a little tiny pebble right above the center. And when you do that, it'll make a little dimple in the middle of this thing, and all of the water that condenses on this plastic over a day's period will force the condensed water to drip into your little container, and it'll fill up, and it'll give you enough water to hopefully keep you hydrated for as much traveling or whatever you're doing. So that's one important piece of survival gear that we'd always want to have. Is another one that I've actually thought about a lot, especially because I go in the water a lot and used to do a lot of fishing and boating, is, I'm getting older. I wear reading glasses to read stuff, and that sounds kind of weird for you young guys who have good eyes still, but one of the pieces of survival equipment that I always packed when I was in the military that didn't come in a normal survival kit was a magnifying glass. And the reason is because if your eye's injured, or if you are older like me and you really need to focus on like a rescue radio and change the frequency and you can't really see it, you can use the magnifying glass. But the magnifying glass is also great for starting fires, for burning holes in things. If you want to drill a hole in a piece of wood, you could actually drill a hole using the sun and burn a hole in a piece of wood. So the magnifying glass is actually a great survival tool. So if you're ever in a survival situation, that's one of the pieces of equipment that I'd always take with me. Another thing I'd always want to have with me if I could is a piece of surgical tubing. Because here in Hawaii, we all know what a Hawaiian sling is. And if you're in a survival situation in an ocean environment or a water environment, or even in a land environment, you want to catch rabbits or squirrels or whatever, or birds, you can use that surgical tubing to make a Hawaiian sling, to make a spear, and go after some small game. And then a Hawaiian sling is a stick with a sharp point on one end and the surgical tubing tied on the other end with a loop, and you basically pull it tight and hold it, and then let go of the spear when it's aimed at an object, and the rubber tubing, all the energy from the rubber tubing will let loose and poke into whatever you're aiming at. It's really, really accurate. It's something that most of the local divers here know how to use, and in a survival situation, that could mean the difference between having some food and not having some food. So there's some great stuff that you can learn, especially if you go back and look at some of our heritage and Hawaiian heritage, and how local folks did fishing and catching squid or octopus using shells and hooks. And there's some great stuff we can learn just from looking at our Hawaiian heritage. So there's some weird science for you to get started. I'm going to come back with some more complex weird science a little bit later on after the break here, and we'll be back in about 60 seconds.
Hi, I'm Stacy Hayashi, and you can catch me on Mondays at 11 on Think Tech Hawaii. Stacy to the rescue. See you then.
Hey everybody, my name is David Chang, and I am the new host of the show, The Art of Thinking Smart. I'm really excited to be able to give you the smart edge in all aspects of your life. Gonna have awesome guests, some of my great mentors in the business, military, political, nonprofit, you name it. So we look forward to seeing you every other Thursday at 10 a.m. on Think Tech Hawaii, and also on my blog, artofthinkingsmart.com. Look forward to seeing you there.
Aloha, I'm Kaui Lucas, host of Hawaii is My Mainland, every Friday here on Think Tech Hawaii. I also have a blog of the same name at kauilucas.com, where you can see all of my past shows. Join me this Friday and every Friday at 3 p.m. Aloha.
Hey, welcome back to Likeable Science, or Weird Science, as we have today with me, Stan the Energy Man, rather than Ethan Allen. And I'm here to talk about a little bit of the science that I used in the military and in flying. And we'll talk about a couple things. I'm actually going to talk a little bit about a fairly, I want to say, complex science, but it's been used for thousands of years by mariners and people who traversed the world before they knew it was round, and that's celestial navigation. But before I get into that, we'll talk a little bit about just how airplanes work and the basic principles of lift on a wing. If you look at an airplane wing, you notice it's curved on the top usually. Sometimes it's curved on both sides. But what you'll see if you have a traditional wing, which is curved on top and flat on the bottom, kind of looks like this. What the physics behind this is as all the air hits the wing and tries to go around the wing, the air that goes underneath the wing and the air that goes over the wing have to meet back here at the same time. So what does that mean? This air has a shorter distance to go because this one's going all the way around the corner and coming in. And so what does that do? That actually creates a low pressure system on this side and high pressure system on this side, and it gives the wing lift. So when you hear of an airplane wing giving you lift, it's because of this principle that the air is going to move and meet at the same time over here, but it has different distances to cover, and that changes the pressure differential on a body, so it actually gives you lift. And that's how an airplane wing has lift. So in an airplane, when it comes to flying, you have several forces. You got gravity trying to keep you down. You have lift from your wing letting you go up. You have acceleration from your engine. The more power you put in, the more you accelerate forward. You have pitch when your nose goes up. You have yaw when the plane turns sideways, and you have roll. So you have different physical factors at work on your airplane as you're moving. So the aviator, the pilot, has to get used to understanding what's at work in his airplane at any given time. So the simple way we used to put it is, when you push the throttle this way, okay, the airplane goes faster and you go back in the seat like this. When you pull it this way, you slow down and you go forward in the seat. When you push the nose over like this, the houses get bigger, and when you pull it up, the houses get smaller. You know, we try and keep it really simple for the aviators so they don't get in trouble. But bottom line is, in an airplane, you have a way of controlling your pitch. And if you do raise your nose and you want to climb, you usually add some power and get the airplane climbing up. And then when you level off, you'll just drop the nose and hold it level, and you can pull the power back and it'll maintain your speed. And you don't even need to have fancy instruments. A lot, the early airplanes that were flying, they didn't have all these fancy instruments for flying in the weather. And when they wanted to stay level, they didn't necessarily have to look at their altimeter. Once they got to a certain level they wanted to stay at, you'd actually look at the shape of your airplane and look at the horizon behind it, and you could maintain almost level flight just by keeping that same sight picture. So there's some great science there that you can learn from the different aspects of lift, drag, pitch, yaw, roll, and that's what pilots live with every day. And the more it becomes internal to you and the more comfortable you feel with what things you do with the airplane that affect it and how they're gonna impact your day. Things like you don't want to be pulling the nose up and not add power, because if you do that, pretty soon you run out of speed and the plane starts falling out of the sky. We call that losing all the lift on your wing as stalling the wing. You don't want to put the nose down and not pull up, or you hit terra firma, and that's not good to run into the ground. So we learn about a lot of different physics in aviation that keep us in the air and keep us going. But one of the things I wanted to talk a little bit about today is celestial navigation. And one of the funny things that we learned when we first start learning celestial navigation in the Air Force is that everything that we learned in the science class was totally wrong. The Earth is flat, and we start from there. And you just kind of go, what? The Earth is not flat, right? Stan, the Earth is round. But for navigation purposes, they teach a couple things. Number one, they teach that if you have I wish I had a ball, a sphere. But if you look at a ball and you imagine that ball as the Earth kind of suspended in the middle of the air, and you looked at all the stars and the sun and the moon around it, you would be able to say that for every star at any given time, there was a point right on the surface of the Earth that was right directly below that star, where that star was right overhead. And there was a spot right on the Earth's surface where that star was directly overhead. And if you understand that the stars and the sun and the moon move in very predictable patterns, what our early ancestors learned about celestial navigation was you could predict where those stars would be at any given time. So what we do now is we have a very sophisticated way of measuring. We know exactly where stars are going to be on any day, at any time, anywhere around the world. And what we do is when we're flying around in an airplane, we'll just say we estimate we're going to be right here on the Earth. That's our spot. We use a triangle for that. We call that a dead reckoning point. And then we pick 3 stars, and we say, okay, I'm looking at this star, and its subpoint, that point right underneath the Earth, is right there. That's directly above that star. And if I drew a circle around that point, the circle would look like that. And then I'm looking at this star over here. It's off in this angle, and its subpoint is over here. And if I took a spot from here and drew a circle, it would be like right here. And then I'm looking at this star way over here, and it's way on that side of the Earth, and its subpoint is way over here. And if I drew a circle around that point, it would be right here. And so what happens is where these 3 circles overlap, guess where they overlap? They overlap right where you're at. And you may think that's pretty weird that stars that are millions and millions of miles away, light years away, could give you a very accurate point of where you are on Earth. Believe it or not, our margin of error for a check ride was 3 miles. And we're doing 400 or 500 miles an hour while we're flying, while we're calculating this. So our position, taking it off of 3 stars to pass a check ride, was 3 miles. I think they'd give you some credit if you were 4 or 5 miles, but if you were 10 miles, you were failing the check ride. And 3 miles was what your target was. So what you're basically doing, if you think about that, the star is like right over your head, and it's straight up and down, and you're drawing a circle around where the star's subpoint is. And if one circle's line is here, or one star's line is here, and another star's line is here, another star's line is here, you'd basically take this side of the triangle and bisect it, this angle, bisect it, this angle, bisect it, and that's the triangle. That's the spot on the Earth where you are based on those 3 stars. Amazingly accurate. And if you go back to early Polynesians, again, they noticed more basic relationships to stars, and they would say that, okay, in the morning when the sun comes up, we know it's going to come up right over in this direction all the time, plus or minus a couple degrees at the most. So they're looking for the sunrise to come up, and at sunrise they take a bearing off of that, and they know the nose of their canoe should be so far off, and they know they're heading the right direction. If they wake up in the morning and the sun comes up and it's way over here and they're expecting it to be way over here, they know they've been off course for a certain amount of time. They'll correct back towards course, maybe overcorrect a little bit, and start navigating back towards where they should be, and then look for other celestial clues to figure out whether or not they're close enough to track. They also use things like rebounding waves coming off of islands. You know, we're used to seeing big waves passing us in a boat, but when you get near an island, those waves hit an island and they rebound back off. So you'll get to actually see that rebound come back into your pattern and say, hey, I know I'm near an island and I'm expecting this island to be over on my left side. Hey, it looks pretty good. I'm getting rebound from that side. Hey, I'm seeing birds that are usually near the islands. That's a good sign. Hey, I'm seeing insects that are near the islands. That's an even better sign. So celestial navigation nowadays is a really precise science, but even in older times, celestial navigation coupled with natural observations of what happens on the Earth's surface could give navigators really, really accurate information as to where they are. And that's why the Polynesians and other navigators actually found their way around the world so well and could repeat it. That's the key, could repeat it so well because they made such great observations on the celestial side and also just on how things worked in nature. So that's one of the concepts that I think most people, they see a sextant, like a sextant that sailors use, and it scares them because it just looks like kind of a weird mechanical thing with lots of mirrors and stuff. But what you're really doing on a ship is you're taking a bearing off of a star this way and a bearing off of a star that way, and you're crossing them to find the same kind of point and giving yourself a position, what we call line of position, that tells you where you're at on Earth. So that's some other great science that we learn in the military for flying, and some great science that helps us out. If you have any other science that you'd like to know about sometime, let us know here at Think Tech Hawaii, and we'll have Ethan Allen answer the question for you because I don't know everything. I'll just have to ask Ethan anyway. But we can call up Ethan and get the answer from him real quick. But there's a lot of fun things. I tell you, one of the things I learned at survival school and I went to survival school like 30 years ago. Here's a really easy knot that I use all the time. So simple. You make a loop like that, you reach through it and make a little thing like this, and what do you got? You have a little slipping knot. You take this end that pulls, that makes it get bigger and smaller, you make a loop in that, and you flip it over and pull it tight on the front side of the knot, and that's called a trucker's hitch. Now it doesn't slide anymore. It's not gonna move. So you put that on one side, and then you have your load in your truck, and you come on this side, and you make a loop in here, and pull it tight. And now you have another little loop, right? And you take this one and do the same thing. You just make another little loop and flip it over and pull it tight, and now it's locked, and you have a really strong connection. And when you want to take it off, you just come over here, pull that little loop off, pull it loose, and you're done. And when you want your rope back in one piece, you pull that loop out, and you're done. Easy to untie, easy to tie, really quick. Another one that's used a lot, especially by mariners, is called a bowline. And so you have a piece of line here that's maybe going out where you're trying to hook onto something. You make a little loop there, and then you take this end, run it through, around, back down through the loop, and pull it tight. And what you have is a good tight loop that's not gonna pull out. But the good news is that when you pull this thing really tight, when you pull it super tight, like if you're gonna tow a vehicle, and you know how much strain that can put on your rope, and it's like, you'd never get the knot out. But this one, actually, the knot comes out very easily, because once you start pulling on the end that, you start pulling on this piece right here, it doesn't cinch down too tight. And once you get one piece loose, everything else just comes right apart. So a bowline is a really, really good knot to use when you need a strong knot that can help you pull something, but you're gonna need to untie it. And by the way, that even works with a cable strap, like a tow strap. If the hook breaks off or something, you can still use a bowline on a regular strap, and it'll come loose real easy. No strain at all taking it apart, even though you had a couple thousand pounds pulling on it. So there's a little bit of likable science from the weird science guy, Stan Energy Man. Thanks to Ethan for giving me the opportunity to talk about some science today. I appreciate it, and maybe when he has a day off again, I'll come back and do some more weird science, if I can think of some more weird science. And if you have some you want, call in and share with these folks, and I'll see what I can do to answer any questions about Stan's weird science on Ethan Allen's likable science. Aloha.